Hi again. This is another problem using, in this case, Coulomb's law, the electric force, and we're going to solve for the force at one of the locations of the charges. So let's go ahead and do that. So what I'm going to do is solve for the force on this top charge here. What's the electric force? So Coulomb's law says that we need two charges to find the force and the distance between the two of them. So I'm going to call this Q1, Q2, and that top one Q3 just for label purposes. So I'm going to go ahead and do that. So I'm going to actually get rid of that and just do Q3. Okay. And I took this from the context of the mastering physics. Each Q is going to be different for you, but for this one it's 7. So let's go ahead and do our steps. The first step is to find the direction of the force for both 1 and 2 on 3. Because that's what the question is essentially asking. So let me just move this 3 over here, I suppose, so it's not in my way. There we go. So these are all positive since they're all 7 coulombs. So this positive and this positive here, if I ignore that one and I look at what they do, it's going to be pushing this one upward, force of 1 onto 3. So this one will be pushing straight up in that direction. Because if this were here and allowed to move, it would be pushed away. Same thing with this one. This one's a positive charge. And if this thing were allowed to be pushed, this would move away at this point too. Force of 2 onto 3 like that. So the question is, what's the sum of these two forces? So step 1, finding the direction. Step 2, let's find their strength. So force of 1 onto 3 and 2 onto 3. Let's keep our notation the same. Force of 1 onto 3 is going to be KQ1, Q3 over R squared. So my force will be this value here, like that. Q1 is 7 microcoulombs, so it's at a -6. And it's the same charge, so I'm going to use that number again. Divided by their distance apart, so they're 15 centimeters apart, which means 0.15 meters for my distance. So I'm going to go ahead and calculate this out. So 8.99 e to the 9th times 7 e to the -6 divided by 0.15 squared. Newtons when I saw about the force value. So that's the value of this one. Now, force of 2 onto 3, we solve the same way. Now, hope you notice that this is going to be really nice because the charges are the same. They're the same charges, the same value because they're all the same charge. They happen to be at the same distance, which conveniently gives us the same answer. So obviously you don't need to show all your work if it's going to be the same, but I'm showing you that it becomes the same. So these are the values of these two forces up here like that. So now that I found the value, now I'm going to break them into their x and y components, F13 x, F13 y. So let's start off with that one. So taking it out of the problem, this arrow kind of looks like that, which means this dotted line will represent the x, and this dotted line will represent the y, like that. So here we go. So remember that this is the hypotenuse value right here. And this will be the hypotenuse times cosine of the angle. We do some trig here. And this is going to be the sine of the angle. Again, I assume the trig is straightforward. Now to find the angle, we need to do a little geometry here. So this angle is the same as this angle because we're making a similar triangle. And that's the one that we have here. Now, since all the sides are the same, we have an equilateral triangle, which makes that 60 degrees. So this will be 19.58 newtons times cosine 60. And this would be the same thing times sine 60. Sorry, I'm kind of running out of space. So I'm just going to write these values down here, although you can get the idea. So the y value is going to be 16.95. Since it's going up, that's a positive value. The x value (9.79 newtons). And since it's going to the right, that's going to be a positive value there. So that's for F13. Let's take a look at F23. F23 looks like this, which means we're going to have a negative x and a positive y here. F23y, F23x. Now notice that this is the same hypotenuse. And actually, this is also the same angle by the same logic up here, right? This angle is the same as this one. This is an equilateral triangle. So that would be 60. So I'm going to use that knowledge to my benefit, which means the sines and cosines here are going to be the same. It's force 23 times cosine the angle. This is force 23 times sine of the angle. So I know these values already, but they change a little bit. So the cosine value was the 9.79 newtons. But this one's going to the left, which makes it negative. This one is the same value, so it's going to be the 16.95. But that's a positive value, so that's going to do that. So my next step, 4, is to add all these values, x's and the y's for the totals, right? So let's go ahead and do that. xy, force of 1, 3, force of 2, 3. 1, 3, we have 9.79 for the x and 16.95 here. This one's negative that value, and this is positive that value. So these are the same values, so that cancels. So the total here in the x direction is 0. And these double, so 16.95, so 33.9 newtons. So if you draw this, what I have is a y value straight up, because these are both positive, which makes this positive, of 33.9 newtons. I can't make a triangle for this, so that's the answer. The answer is 33.9 newtons upward. That's because, again, our x values canceled out. So here's an interesting case. If all the charges are the same, located at the same distance with the same angle, if everything is the same, then this charge will move straight up. And that's the net force of this, the 33.9. No angles needed because up is fine. I mean, if you want to be official, it is officially 90 degrees. But the problem will demonstrate it and have it go straight up. So This is fine, in terms of the process. But remember, if you don't have one of these values, then it's going to be purely up, down, right, or left, and you don't need to do a triangle. So we're done with the problem right here. So that's our final answer. 33.9 upward is what this charge would feel if we allowed it to be moved and to be pushed.